Okay, welcome. It's 8 a.m. on a Thursday morning. We're back here at Organic Chemistry 2341. Our section is 253. So what we're going to do today is we're going to continue on with Module 2 or Chapter 2 in the book, which is nomenclature. Okay, so one of the things we're talking about today is we're talking about the nomenclature of hydrocarbons specifically. And remember, those are the ones with only carbon and hydrogen bonds. And we have learned about our prefix, infix, suffix. Okay, so with our hydrocarbons, our prefix is all of the substituents plus the number of carbons in the parent chain. So that's going to be, your substituent methyl, 2-methyl, and then your carbon chain, which is the penta, that's in your suffix. Your infix is going to be whether it has a single bond, a double bond, or a triple bond. Okay, it says my Wi-Fi is unstable. I'm going to switch over to my other Wi-Fi. Hang on, please. There we go. There we go. All right, I'm switched over to my other Wi-Fi, so hopefully that'll make it better. Our infix tells us whether we have single, double, or triple bonds. So our infix is AN with a single bond, EN with a double bond, and YN with a triple bond. And because hydrocarbons are our simplest and lowest priority system, the E at the end is actually our suffix, telling us that it's just a hydrocarbon. If it's anything other than an E at the end, it's something other than a hydrocarbon. So those are the three things that tell us what to do, okay? So let me start sharing my screen to make sure that everybody can see me. We're up to 54, that's not bad. All right, let's see. All right, can everybody see the screen now? It should be on the alkenes, the stereochemistry alkenes. All right, excellent. Okay, so I wanted to go over this one more time. In our alkenes, the priority has everything to do about 1/2 of the molecule and the other half of the molecule, and just comparing the two that are the highest priority on either side. So make sure you follow that procedure where you take, you cut the molecule in half right here, and then you find out which side is the highest priority over here, okay? And so if this is the highest priority on this side, you're done. Now you go to the other side and find out which is the highest priority, and this is the highest priority because it's all about atomic number, not atomic mass. That'll mess you up a couple times. Atomic number. And now that we have our highest priority on this side of the molecule, and they're both on the same side of our thing, we can call that our Z. Zusammen, same side. If they were on opposite sides, so one was down here and one was up here, we would have to use the entgegen E term. It's best to use E and Z if you have any more than 2 attachments, okay? Cis and trans works just fine if you have 2 things on your double bond. If you have more than 2 things on your double bond, you should use the E and Z terminology, okay? So, and again, if you can't tell it immediately by what's attached to the double bond, you keep going out until there is differentiation, okay? So for example, when we did this one with carbons, we kept going out until there was something that wasn't the same. We had a carbon here and a carbon here, a carbon here and a carbon here, but we had a carbon here and we only had a hydrogen here, making this the deal breaker, making that the definitive answer and making that our higher priority. So it's all about atomic number, and you keep going out until there is a differentiation. Once you have a single differentiation, you're done. You can assign priority. All right, questions on cis and trans alkenes? Oh, there is. Why? Okay, there's people in the waiting room. All right, there we go. Okay, no questions. All right, then let's move on to our next. Okay, so let's look at our alkynes. Okay, so our infix here is YN. It tells us we have a triple bond. The E tells us we have only hydrocarbons. Okay, so when hydrocarbons contain at least 1 triple bond, so it can have more than 1 triple bond. It can even have double bonds in there. We have to use that "-ine" in it, the name. Okay, so the "-ines", because we had a double bond took us down to the CN, H2N, we have to lose 2 more hydrogens to create that next pi bond. So that makes our generalized formula Cn, and H is 2n minus 2. So if C is 10, then our H is going to be 20 minus 2, which is 18. Okay, and so that's an easy way to remember that. Just looking at your formulas right there, you can tell that you have something that is not a fully saturated hydrocarbon. Okay, now when we name these alkynes, the triple bond, both carbons in the triple bond must be in the parent chain. Okay, so even if you can find a longer alkane chain somewhere out there, the fact that the alkyne is higher priority means you have to have both carbons of that alkane in the parent chain. Okay, so let's look at that. So if you just looked at this and said, oh, great, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's my longest chain is 10, right? Well, that would be true if you didn't have that alkyne in the system. So we can't use that numbering system. We have to include both of the carbons in the double bond, triple bond. So we're going to start at one of the carbons, and then the next carbon is going to be next in the chain. It doesn't have to be at the end. I'll show you how you can differentiate that. But now we have to go from, once we've gone through these 2 carbons, we have to then find our longest chain from there. And that happens to be going to this side, which would give us a total of 8 carbons. This side would only give us 7 carbons. So now we know that we have the octane is the octa is our prefix here. And now we also need to identify where our substituent is and what our substituent is. So since our substituent is the chain over here in red, we see that it has 4 carbons in it. So that makes it butyl group because it's that butyl group. And because we have to also start numbering from putting the first carbon of the alkyne at the lowest number, we also know we have to number from this side, which gives us our location of our substituent as 3. So that gives us our first component here, our substituent in our prefix, which is 3-butyl. The second component in our prefix is our octa, telling us we have 8 carbons in our main chain. All right, now we have to identify the location of our alkyne. Now, usually if it's at the beginning of a chain, like the 1 position, you can leave the 1 out. However, I'm going to include the 1 here so that if it's in the middle of the chain, you'll see where it could be. All right, sorry, admitting someone here. So that being said, we're going to, of course, separate all letters and numbers with a dash, -1, because the first carbon is in the 1 carbon, dash -ine, and then E because it's a hydrocarbon only. Okay, so does that make sense? So we're using all the same rules. We're just figuring out what the functional group is, and the functional group tells us what that last part of the word is. The infix and the suffix have everything to do about the functional group. Okay, so now what if you have multiple double or single bonds? Well, that's fine. Anytime you have multiple things of the same group, just like 3 methyl groups can be trimethyl, if you have 3 of the same bonds, you can actually call them di, tri, tetra, as many as you have. So, for example, a compound with 2 double bonds will carry the suffix di-ene. Di for 2 of them, ene for being a double bond. If you had 2 alkynes in the same main chain, you would have a di-ine, okay? So you can do that as many times as you want. 4 of them would be a tetraene. 5 of them would be a pentaene, okay? Now, you have to remember that you can only use the multiples if all of those double bonds are in the same chain. Okay, so it gets a little complicated once you have more than 1 or 2 in here. So let's kind of make sure that we can follow all our rules. So our first rule is to find the functional group. In this case, we have an alkyne. Okay, we don't just have 1 alkyne, we have 2 alkynes. So we know at the end of the word, we're going to have something like di-ine. Okay, so let's write that down, make sure we remember that. Okay, now let's find our longest chain. We can start from, if we started from this end, we would still only get 7 carbons. So we're going to end up with a total of 7 carbons. So somewhere in our name, we have hepta. Okay, so that's the prefix in our system that tells us the number of carbons. Okay, now we have 2 substituents there that are not included in here. They're right here and right here. Now, this is numbered such that the first alkynyl carbon is at the lowest position. That's why we started here. We did not start here because that would have put the first alkynyl carbon at 3. So we must start on the side that gives us the lowest number for the alkynyl carbon. And that also puts us right here at our substituent 3. Okay, remember that, because if we just looked at giving the substituent the lowest number, we would have started on this other side. So make sure that you always put the alkene and alkyne first carbon as the lowest number possible. Okay, so we have 2 of these and they're located at 3 and 6. So that gives us a 3,6-dimethyl. All right, so let's put it all together. 3,6-dimethyl hepta. And, oh, we've got to locate the alkynes. So the first alkyne has its first carbon on the 1 carbon. Then we have 2, 3, 4. And the second alkyne begins on the 4 carbon. Okay, so we only use 1 of each of the carbons in the double bonds and triple bonds to locate it. So we have our hepta for 7 carbons dash 1,4-diene. And again, at the E here means it's only a hydrocarbon. Okay, so see how we're following all those rules and we are not, you know, and every time, even when we add additional functionalities, we still follow all the rules in the same order. We just add another rule as things get more complex. Okay. So what's next? There we go. Well, what if you have double and triple bonds in there? Okay, because the double bond gives you the infix of -ene. The triple bond gives you the infix of -ine. But because they're both in there, you actually have to include both of them. So they're what we call ene-ines, okay? Because neither one is above the other in priority. So we have to actually put all of them in it. So we have to include where the enes and the ines are. Now, enes are slightly higher in priority than ines, meaning that if you have an alkene, you want to put the lowest number possible on the first carbon of the alkene, okay? But you have to represent the alkene and alkyne in your system. So when we number that, in this case, we don't have a branch point here, but we do have the idea that our alkene is going to be in the 2 carbon. If we named it from this direction, our alkene would actually end up with something like a 4 carbon. So we're numbering it in the direction of having the alkene have its first carbon be the lowest number. Now that makes our ene on our 2 position. So we can say our 2-ene as locating this functional group. And over here, our first carbon, now that we know we have to number in this direction here, is at 5. So now we have our 5 locating where our ine is, okay? And since we use ene as slightly higher priority because we're using that for numbering, we're gonna put it first in our name, okay? So now let's add it all together. We have a total of 7 carbons, which gives us hepta. And we put the ene first, so it's 2-ene. And the ine last, 5-ine, okay? So now we do have stereochemistry here. So let's double check our stereochemistry here. And if we look at our double bond here, we have only 2 things attached. So it's okay to cis and trans. We don't have to use E and Z. So in this case here, we split down the middle and the 2 different substituents are on the opposite sides of that double bond. Therefore we have trans. So our total name is really trans hepta 2-ene dash 5-ine. Okay. Okay. And if this substituent was up here on the same side right there, we would name it cis. But the true name for that. So the key thing to remember here when we have double and triple bonds is you put the ene first, and it has the lowest number, but you also have to include the ine. Okay. All right. So that takes us out of all the hydrocarbons. Our hydrocarbons started with alkanes. We had to talk about cyclics and bicyclics. Okay. And then we went on to alkenes, alkynes, and things with multiple double or triple bonds. Okay. So we would just extend all these same rules, even as the molecules got more and more complex. So now let's talk about how we name the other functional groups that aren't alkanes. Once we stop having things that are alkanes, we have to change that last letter, which is the suffix that tells us what the functional group is. So always looking at the end of the molecule is going to tell you something about the highest priority functional group. So let's go back to that functional group list here. And again, we're only going to be learning up to probably aldehydes and ketones this semester, which is, let me get my pen up here. It's going to be from this, oh, that's not showing up very well. Let me do red. This section here, these are the ones that we must know for this semester because these are the ones we're actually going to use. Once we get into next semester, the carboxylic acid and the carboxylic acid derivatives, that's when we'll actually start using those. But these are the ones that we need to focus on specifically for this semester. So if our functional group is a good leaving group like a halide, we call them alkyl halides. Alkyl halides never change the name of the thing. It's named for the longest carbon chain, and you put the "-il on it and add chloride. This is the way we name it as a common name. It could also be named 1-chloropropane. That is the IUPAC name. So halides don't change the name. It stays the hydrocarbon or alkene that it is, or and it changes. Sorry, it stays as the hydrocarbon it is. It does not change the suffix. Okay. Now, once we form our first double bond, we now change our infix in keeping our suffix because we only have carbon and hydrogen bonds. We change our infix when we go to our alkynes, and we keep our prefix because we have that. Now, alcohol is the lowest priority group that changes the name. We take that E off and we add OL to the system, and I'll talk about that in more detail as we go through these all there. But ethers, on the other hand, the oxygen and the carbon chain on the ether is a substituent. It does not change the name. We're actually going to show you the common name and the IUPAC name for that. Thiols are like alcohols. They change the name. The E is going to be dropped off the end, and we'll have a word for that. Sulfides are substituents. Now, when we get up to aldehydes and ketones, the ketones are going to change the name. Our suffix is going to end up being ONE, and our aldehydes are going to end up being AL, al. So we're going to see that change. And so those are the ones I'm going to go over, but I will also go over quickly the naming structures for these as well, just because we're going to be using some of these as reagents on our reactions, and I kind of want you to be exposed to their names, and so you can quickly figure out what they are. So the next thing we know is that there's a certain priority. If we have only hydrocarbons, we know we have an E at the end. And then as we add functional groups like the amine, these are going to be, typically we can have a suffix for them, which is where we have the amine at the end, where we have in the common name like an amine or esamine. Then sulfur and oxygen will change the name. And then once we get to the ketones and aldehydes right here, that's where they also start changing a lot. Now, if you have something that is, if you have two substituents, let's say you have an amine group and an alcohol group on the same thing, okay? Which one gets the suffix? Well, the one that gets the suffix is the one of higher priority. So the alcohol it'll be named for the alcohol, we'll have the OL at the end, and we have to designate the amine here as a substituent. Okay, so once you have something above it, that names it, and everything below it is a substituent. So notice that halogens and alkyl groups and alkoxy groups are all below hydrocarbons. They are always substituents. Okay, so we'll continue on that, and I'll explain those rules as we go to the next thing. All right, so again, we have our substituents, prefix, infix, and suffix. Suffix tells us the highest functional group of our compound. And so far, we've been using the E, which is only for hydrocarbons. Oops, gotta let somebody in the room here. All right, so the next thing up from there is the amine. The amine is our next functional group above an alkane. It's the one thing that changes it. And the cool thing is that most of the time, do we need them? You need to start learning them now. I wouldn't say memorize, but yes, start learning them now. And remember, go to Canvas. There is a review of organic nomenclature set that has all these rules enumerated in order and the priorities, as well as there's a flyer in there for functional groups you need to know with their generalized structures. All right, so we're going to use all the same rules we have, but now that we have an amine, we know we're going to change the name. And our amine is the highest functional group because we only have hydrocarbons. Amine is the one thing above hydrocarbons. So we get to add amine to our name, okay? Amine, okay? And because it's naming the compound, we always start numbering from that, okay? So that means if our amine is here, where you know where we start. We must start from where we're naming the compound. So if this was an OH, we would start from there. If that was the carboxylic acid, we would start from there. So you always start from numbering the carbons from that naming functional group. So it's not as ambiguous, it's not as unambiguous as it is for hydrocarbon. It's very fixed. Okay, so we're gonna have one amine as our end name. So that's our suffix. So now we find our longest parent chain associated with it. And let's start counting. We have 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7. So both of those chains are exactly the same length. So one of them becomes a substituent and one of them stays the parent chain. So we have a total of 7 carbons in our parent chain. So we have hepta, okay? But we also have no double bonds and no triple bonds. So we have ane. It's a hydrocarbon, still has an ane. We always have the ANE, the AN, EN, or YN, even if it's named for a different functional group. If there is a triple bond in there, if there was a double bond, we'd have it heptene 1-amine. If we had a triple bond in there, we'd have heptyne 1-amine. Okay, so we still include this because we only have single bonds. And then we have, since that is no longer the main chain, we got to number that. And that is 1, 2, 3, 4. So that's the butyl chain, and it's located on the number 3 carbon. So our name is now 3-butyl heptane 1-amine. Okay, so that's the first functional group above the alkanes and alkynes. But all we're dropping is the E and adding our functional group. Okay, we still keep the AN, the EN, or the IN if needed. All right, our next functional group. All right, so now we're going to talk about how to prioritize things when we have more complex organic compounds, okay? So we're adding on another rule here to look for different things, okay? So in the case, if more than one parent chain exists, you choose the parent chain that contains the greatest number of multiple bonds, either double or triple bonds, okay? Why? That way we can use the word diene or triene or whatever in our main name. And so that becomes our parent chain. The parent chain with more functional groups is the priority parent chain. So in this case here, even though we can get a longer chain by going down here, that would leave us with a substituent that would be difficult to name right now because we don't know what that group is. So what we're going to do is we're going to instead choose the parent that contains both of those functional groups. And because we are looking at that now saying, okay, how do we number that? Well, we have to number it so the substituent's on the lowest side, but we also need to have the first carbon of a double bond also be on the lowest side. So we could number it from this way, but that makes our substituent on the 4 carbon. So that tells us we need to number it in this direction here. So we still have a 1 on our alkene, but we have a 3, the lowest number for our substituent, giving us a 1. Let's see, that's 4 and that's 5. So we have a 1,5-diene right here, and that's just our main chain. And then we have this propyl substituent on that 3 carbon, 3-propyl hexa 1,5-diene. Oh yeah, carbon number 6 there. Okay. Now, remember when we have multiple choices for substituents, this is the same rule we had before. So if we have an amine that's changed the name, we know the nitrogen, the amine has to be in the main chain. So we use that same rule where we choose the one with the greatest substituents. Okay, so just like before, when we had those hydrocarbons, we try to find the longest chain with the greatest number of substituents. We still do that with the amine, but the amine has to be in that longest chain, whatever's changing the functionality has to be in that longest chain. So it follows that same rule. It's just now we know which chain we have to label first because it's the one that changed the suffix. Okay, so now let's say you have your parent chain was named for a hydrocarbon like alkene, alkane, alkyne. Once we change that functional group, that suffix is part of the highest priority functional group. So in the case of the carboxylic acids, we actually end up dropping the E and adding oic acid to the end of the compound, okay? So now whatever that functional group that's changing that name must be in the parent chain, even if you can find a longer hydrocarbon chain. We can find a really long hydrocarbon chain here, but it does not contain the name changing functional group. So that can't be our source. So if we go to the one it is, we start at the first carbon in that chain. In a carboxylic acid, it's actually the carbonyl carbon, the carbon with a double bonded to oxygen, okay? So we always start numbering from that functional group, and then we find our longest chain, okay? In this case, we have a total of, we can only find 2. We could number it in this direction here, but then we'd have a weird substituent. So we're gonna number it this way so we have the highest number of substituents, okay? So that's why we would number it that way. And then that makes us to have a total of 2 substituents. And because we had to start numbering it, the functional group, we know exactly which way to number. Our first substituent's on 2, our second substituent's on 3. And so we end up with 2 substituents. One is a P for propyl, one is an E for ethyl. We put them in alphabetical order, and our name is 3-ethyl 2-propyl propionic acid. Okay, so notice it doesn't matter how complex this gets. If we follow the rules in order, we will get to the correct name by doing that. Okay, so let's think about a couple other things about that. So when you have another functional group in the main chain, you always want to get that functional group that changed the name. In this case, we're looking at a ketone. And I think these slides are out of order. I should have gone over individual ones, but okay, I'm gonna continue. This is the C double bond O is our carbonyl, and it is a ketone. And so we have ketone. And it turns out the ONE is what we name it for. So we actually drop the E and add an ONE at the end. But whenever, again, this ketone is changing the name, so it has to be located on the smallest number possible. Ketones can never be on number 1 because that would be an aldehyde. So we can typically have them anywhere from 2 on, but we want to locate it on the smallest number possible. And when we do that, even though our substituents here are higher numbers than we would expect at 5 and 7, the ketone is the controlling factor. It changed the name. It has to be the priority. It has to be the lowest number. Okay. Now, the next thing we need to work on is if that functional group is equidistant from both ends, then the substituent controls which side you, wherever the lowest substituent is. Okay. All right, so I'm going to come back to those rules after we go over the individual functional groups. There we go. Okay. No, okay, sorry. I have to do this here. All right. So in this case here, when we have our double bond here, which is what we're naming our compound for, so we know we have an ene. And no matter which way we number it, it's going to be a 5-ene, okay, because we can number it from both directions to get to a 5 in the middle. We now have to look at the numbering on either side based on the lowest possible number substituent. And in this case, it would be 3 for this group and 3 for this group. So that doesn't tell us anything. So our rule is lowest number based on the functional group, the thing that changes the name. Lowest group on first substituent, unless they're the same. And now if they're both, the substituents are still in that lowest number, we go by alphabetical order. So the prioritization of that goes, so that means that the ethyl group is lower in the alphabet than the methyl group. Therefore, we number it from that side. So the ethyl group is numbered that way. So in this case here, we have the 3-ethyl group. So we have 3 ethyl. We have 3 methyl groups, one on the 4, one on the 7, one on the 8. So it's 478-trimethyl. We have a total of 10 carbons. So that's deca. We have an alkene that starts on the 5-carbon, 5-ene. All right, now we've got everything located on there. Now we have to figure out stereochemistry. And both of the substituents are on opposite sides of the double bond. So it gives us trans. So that means by following all those rules and adding that alphabetization now, we now have a fully correct name for this thing as trans-3-ethyl-5,7,8-trimethyl-dec-5-ene. Okay. And I'm hoping when I say the dash and commas, it'll show up on the YouTube subtitling, so that it makes it easier to follow. All right. Now, remember when we had rings, if we only had one thing in that ring, one appendant to that ring, that is always the number 1 location. If you have a functional group that changes the name of the ring, that carbon is also the number 1 function. Okay. So, and then we go and you number it to find the lowest number for the different substituents. So for example, if we have this one in the middle here, because the ketone here changed the name, and you can tell that because you have an O-N-E at the end here, this ketone changed the name, that means that's always going to be the number 1. And then we number to find the lowest substituent. So it's 3 if we number it in this direction. It's actually 5 if we number the other direction. So that must be our 3 substituent. Okay. Now notice if we have this is also changing the name here, but our first substituent, our first differentiation here is that first carbon of the double bond. So we have to number it so that double bond is now at the lowest position, making our substituent in the 5. So notice it's the first substitution or the first differentiation between the other carbons, and that happens to be the alkene. So we have our 1 as our ketone, so we have our own, and then we have a methyl group out on our 5-carbon. So we have cyclohexa-2-ene own. It's hard to say fast, but it is the truth. And then if we have 2 substituents that are at the same location, it's 3 on, if we number either direction, we do it in alphabetical order, just like the previous slide. So we number from this direction, giving our lowest alphabetical substituent the first position, and our next substituent the next position. Okay. Do you see how the rules are really consistent within themselves? We go through priority, lowest number, alphabetization, alphabetization. So in each of these, it goes in that same order, even though you're going deeper and deeper into a more specific chemical name. All right. So let's go crazy. All right. So we have a bromo group, we have a hydroxy group, and we have a ketone here. Okay, bromine never changes the name. It's always the bromo, whatever the alkane is. So that's not the highest priority. Alcohol is above that. We could have an alcohol in that, but when we look at the priority chart, the ketone is highest. So that means our ketone is our starting point. So we start here and we look at that as our number one position here. Okay, so we have on at the end. We also have a 6-membered ring, so we have cyclohexane. Do we have hexane? Yeah, we only have cyclohexane. We're going to drop the E because the ONE is going to be at the end. Okay, now we start finding our substituents. Okay, on our substituents, okay, if we numbered this way, there is not a substituent here, so we must number to where the hydroxy is first. It's the first substituent, and it's the one we're going to name first. So we have to go in that direction. So that gives us 2-hydroxy because it's on the 2 position. And our next substituent is a 3-ethyl right here. This is a 4-propyl and a 5-bromo. Okay, so we've found our parent hydrocarbon, which is cyclohexane. We found our functional group, which is one, a ketone. And now we've identified the location of all our substituents, okay? Now, all we have to do is put them in alphabetical order, and we have correctly named our system. So I think it's gonna be, let's see, 5-bromo, 3-ethyl, 2-hydroxy, 4-propyl, cyclohexanone. Okay, let's see if we're right. 5-bromo, 3-ethyl, 2-hydroxy, 4-propyl, cyclohexanone. Okay, so we followed the same rules every time right there, and we can name very complex chemicals now just by following those rules. Okay. And an even simpler one would be this, where we have the OH on the end here. So, but again, we have to name our thing that changes our name first. So our 2-one is required here, and the substituents are the 4 and the 6. All right. So I think that by following, so why isn't the 1-one at the end? When you have a ring, or when you have a ring like that, you always assume the functional group is on the 1 position. So you can add it, but, and it's more precise, but it's not required. Why is the substituent named propyl? Well, we have, right over here, we have 1, 2, 3 carbons, and it's methyl ethyl propyl, so that's 3 carbons is the propyl. So if it was the chain and not the ring, would it have the 1-one at the end? If it's the chain, right here, the ketone can't be at the end because that would have a hydrogen. It has to be bonded to 2 carbons. And so we actually have to locate the 1 at the end. Okay? On this one. All right. Okay. All right. So, like I said, certain things never change the name. They are always a substituent. And we follow all the other rules first about putting the lowest substituent first. Okay. So in this case here, nitro is a substituent always. And this benzene ring over here is called a phenyl group. It's always a substituent. However, we're putting them in alphabetical order. So MNOP, so the methyl group is going to come first. So that means our methyl group is alphabetically first, and we number from this direction over. So between phenyl and methyl, we have MNOP. So methyl comes first, and so we end up putting that substituent there as well. So we have, and then we have a total of 8 carbons to give us octane. Okay, so and chlorides are the same way. The chlorides also do not change the name. Whoa. All right, so now let's talk about halides, okay? Alkyl halides, we have a bunch of different kinds of them, and we have to know where they are in proximity to other carbons because the hydrogens and carbons that are next to them have different reactivities. So what we want to do is be very specific about where our halogens are. So the first thing we need to know is that the carbon that the halogen is directly attached to is called the alpha carbon, okay? So if we have a halogen, CX, with a hydrogen on it, the carbon it's attached to is called the alpha carbon, and the hydrogen that's attached to that carbon is called the alpha hydrogen, okay? Now this is for, we're gonna see this again and again when we describe these reactions, because sometimes the alpha hydrogen reacts, sometimes the beta hydrogen reacts, and sometimes the gamma hydrogen reacts. So we need to be careful about how we do that. The betas are the carbon 1 over from that, the carbon and hydrogens 1 over from where the halide is attached. And the gammas are 2 over from that. So we can easily tell the difference between the alpha and beta carbons, the alpha and beta hydrogens, and know what they have. Now, the other thing we have is we also have the priority of them in the fact that it depends on how your halide is attached. So if we had the halogen, let's call it bromine here at the end, that is a primary halide because this is a primary carbon, okay? If we have the halogen hooked to a secondary position, that's a secondary halide. Notice that this carbon is a secondary carbon. And if we have a tertiary carbon and we have a halogen attached to it, that becomes a tertiary halide, okay? Primary halides, secondary halides, and tertiary halides all have different reactivity. Now notice there isn't a quaternary halide because a quaternary carbon is one with 4 carbons to it. There's no place for the halogen. So we only have primary, secondary, and tertiary halides. Okay, so let's name them. So naming them is pretty easy because if they're in a hydrocarbon chain, they don't change the name, they're always a substituent. So in this case, we would have the longest chain here. Now notice if we numbered from this side, from this side over here, we would have the methyl group at the 2 carbon, and we have the bromine if we label in the other direction at the 2 carbon. Why do we label it from the right to left? Because bromine is lower alphabetical order than methyl. So bromine is determines which direction we number it. So in this case, we would have 2-bromo, 3,4-dimethyl pentane. Okay, so let me write that out. We have 2-bromo, 3,4-dimethyl pentane. No double bonds, no triple bonds, and the bromine takes priority because of its alphabetization. Okay, now if there's a double bond present, we have to use the double bond rule first. So in this case, we want to put, of course, the double or triple bond at the lowest number possible. In this case, our 2 has to be on this first carbon of the double bond. So that controls our nomenclature. We again still have 5 carbons. So we have pent-2ene at the end of our reaction. That tells us unambiguously that the bromine is now on the 3 carbon. So we have 3-bromo. And notice there's no space here. Bromo and pentane run together. The prefixes run together. And now we have to determine the stereochemistry of this. Okay, so we have 3 groups attached to our alkene, which means we have to prioritize. First thing we do is cut the molecule in half and prioritize both sides. So we have a carbon here and a hydrogen here. So that makes this our first priority on this side. And if we go to the other side, we have a bromine and a carbon Bromine has a higher atomic number, therefore its priority here. Okay, so we're done here. Priority here, priority here. They're on the same side of that double bond, which makes them Zusammen. So our full name is bracketed Z dash 3-bromo pent 2-ene. Okay, so again, halogens are always substituents. It's just you need to follow all the other rules to make sure you put it in the right number. Okay, so I said also ether are also always substituents. Okay, so what we're going to do when we name ethers is we have two ways. We have the IUPAC name and we have a common name. So the IUPAC name would be you take the longest carbon chain and make that your parent. So in the parent down here, it's your longest carbon chain. And then the oxygen and whatever chain is left, the carbon chain there, is the substituent. Now note, the oxygen doesn't count in parent chain calculations because it is not a carbon. So don't count the oxygen as part of a chain. It's named in the chain, but it doesn't count toward your parent chain. So that means in this case right here, we have 4 carbons versus 2 carbons and an oxygen. So our parent is going to be butane. And now we have to name the substituent. Now, when we had 2 carbons as a substituent, we called that the ethyl group, okay? However, if there's an oxygen attached to it, we now change it to oxy, okay? So this is if it was just the ethyl group here attached to the parent chain. Once we have that oxygen making that bond to the parent chain, we now call it oxy. So we have eth for the 2 carbons, oxy for the oxygen as a substituent, and now we have 1-ethoxybutane. Okay. So notice again the suffix and the prefix run together. Okay. So and if we had a common name, all we do is name the 2 different branches. So it'd be ethyl butyl ether. But I don't think that's in the book, so don't worry about that one. All right, our next highest functional group now, this is the first one that changes names, and we call that, actually technically it's the second one to change the name, the alcohols, okay? So in the alcohols, we drop the E from the hydrocarbon and replace it with OL, okay? So just looking at this compound here, we know that we're gonna have an OL at the end, okay? And we're probably gonna put a dash there because we need to locate where that OH is. Okay, so in this case, because the OH changed the name, we have to have it on the lowest number. Notice there is an alkene there. The alkene is lower priority. Therefore, the oxygen tells us where we're going to put our lowest number. And so in this case, we have to number from this side as a 3. If we numbered from the other side, it would be a 4 to give us our longest parent chain. So if we do that, that locates our oxygen here on the 3 position right here. So let's start naming everything else. We have 1, 2, 3. We have 2 substituents now at methyl groups at 4 and 5. So we can do 4,5-dimethyl. Okay, and we have hexa because we have 6 carbons. But now we need to locate the alkene as well. So the first carbon of the alkene, the lowest number of that alkene is 4. So we say -4-ene -3-all, okay? So we used to call this the ene-all rule, meaning that you always have that infix there, because that infix tells you about carbons, but the all tells you about the functional group, okay? Questions on that? Okay. So alcohols also come in primary, secondary, and tertiary groups, okay? And it's all depends on what the carbon is. So if you have it on a primary carbon, it's a primary alcohol. If you have it on a secondary carbon, it's a secondary alcohol. And if you have it on a tertiary carbon, it's a tertiary alcohol. So it's all about the nature of the carbon the OH is bonded to. Okay. So now we're going to move on to a whole set of things, and they all involve the same functional group. And we have what we call the carbonyl group, the carbon-oxygen double bond. This is a very functional, very useful, and very diverse functional group, and it has really cool chemistry because when we learn a little bit more about it, because of what we know about polarity and the fact that the oxygen is more electronegative, this is a very polar bond first, and it has a double bond and it has a pi bond. So that gives it really cool reactivity. Everything in this reactivity about this group is about the polarity and the double bond. So that's why it's kind of diverse. Now, they're broken up into a bunch of different classes based on what's attached to the carbonyl. Okay, so if you have one hydrogen or more attached to the carbonyl, you have what we call an aldehyde. If you have two carbons attached to it, that's a ketone. Now, all these other ones are a carbonyl with an electrophilic atom attached to it, an oxygen, a nitrogen, etc. Okay, or a halogen. So all of those other functional groups are denoted by the fact that it's not carbon or hydrogen. Okay, so aldehydes have at least one hydrogen to the carbonyl. Ketones have two carbons on the carbonyl. All right, so let's go into that a little more detail. When we have an aldehyde, aldehyde is higher than ketone, and it's actually higher than alcohols. So it changes the name. And because it changes the name, we always start numbering at the aldehyde. Okay, so it's not ambiguous. We always start numbering at the aldehyde. So we're going to start with our 1 here. And so our first substituent's at 3, and then we have our 4 here. Okay. When we had the OH and it was the highest priority, we had all at the end. Okay. It's now a substituent. We have to change the name. The name for the OH, when it's not changing the name of the compound, is called the hydroxy group. So we know where it is, and we know what our substituent name is. Now we alphabetize, and we end up with 3-ethyl dash 4 dash hydroxy hexane, because the AN tells us we have no double bonds, and we drop the E and add AL at the end. Okay, so if you had just this compound here with the hydrogen drawn in, that would be 1, 2, 3, 4 carbons. So it'd be butanol. Okay. Now, if we have an alkene in there, we have to include that in our infix, and it'd be butenal. So we can't forget that infix is part of what the carbon-carbon bond, but the Al is telling us we have an aldehyde. All right. Okay. All right. So those are aldehydes. Now these are ketones. Okay. So a ketone, because it's changing the name, right here, we try to locate the ketone at the lowest number possible. So that gives us an unambiguous place to start. So we're going to start at the one end, giving the ketone the lowest number. And then, oh, that's cool. And then, so we have 2 substituents. We only have 1 substituent. We have a bromine, and we've located it on the 3 carbon. So we're going to have a 3-bromo something. Okay. But we have an alkene here that starts at 4. We have to make sure we note that. But we have a total of 5 carbons. So we have pent somewhere. Okay, so let's put it all together. We have 1 substituent, so that's 3-bromo. Pent, we have to locate where the alkene is. 4-ene, so it's dash 4 dash En dash, where is the ketone? On the 2 carbon, so 2-one. Okay, see how they all follow the same pattern? They all follow the same pattern. You just have to figure out what the higher priority group is. Okay, so carboxylic acids are by far the highest priority thing almost always. So if you see a carboxylic acid, it will be named for that. Okay, and because it's named for the carboxylic acid, you always start with the carbonyl carbon as carbon number 1. So rarely do you have to say, if you just have 1 carboxylic acid, you have to say where it is, because it's always number 1. Okay, so in this case here, we have a total of 6 carbons. So that's telling you we have hexanoic acid. Okay, but it would be hexanoic acid. However, we have an alkyne. So that means we have to change our infix now, and we have to show where our infix is. So we have it on the 2 here. So we have to have a 2-ine in there. So we have to drop the E and add the oic acid. So we have 2 in oic acid right here. And let's see, we have this OH is part of the carboxylic acid naming, so we don't name that. We have 1 substituent of bromine on the number 5. So we have 5 bromo hex 2-ine oic acid. Okay, because we drop the E and add oic acid to the end. Okay, now when we move on to other functional groups like esters and things like that, we name them for the carboxylic acid portion and the group attached to it. Okay, so we actually name it with 2 separate words. The first word is what is the parent with the carboxylic acid, and then we have O8 added to it. So whatever the parent alkyl group with the carboxylic acid is called the O8. And whatever this is, it's used as a substituent, an alkyl substituent on it. So if this was an ethyl group, it'd be ethyl alkanoate. So let's do a specific one here. Right here. What we have to do first when we look at an ester is we have to figure out which side is the carboxylic acid. Okay, so the first thing we look for is where is the oxygen and where is the carbonyl? This right here is our carboxylic acid part. So the oxygen and carbonyl are the carboxylic acid. What that means is that this half is the carboxylic acid and will have the O8 part of it on it. And that means this is the substituent. So in this case, we have 2 carbons in our substituent. So we have, let's see, ethyl, because it's 2 carbon substituent. And we have 1, 2, 3, 4 carbons. So a 4-carbon carboxylic acid would be butyl, drop the E, add oic acid. Right here, butanoic acid. But because it's now not a carboxylic acid, it is an ester. We drop the oic acid and add O8. So we come up with butanate, ethyl butanate. Okay. So the first thing you do is you find the carboxylic acid, name the carboxylic acid, then change that carboxylic into O8. And the other half of it, you draw it as just an alkyl substituent, or name it as an alkyl substituent. Okay. So the next functional group here is what we call an amide. Okay. So this is like a carboxylic acid derivative, but instead of having an oxygen here, we have a nitrogen next to the carbonyl. Okay. So that's a functional group that we will get to in the next semester. However, knowing how to name it is pretty much the same way. We need to figure out what the carboxylic acid is first, and then we add amide to the end. So we find out what the parent carboxylic acid is. So if it was 5 carbons, it would be pentanoic acid. And so we know it's going to have pentane, and that we would be having the word amide tacked on the end. So let's figure out exactly what our carboxylic acid is. So again, we're starting with our carboxylic acid as number 1, and we have 1, 2, 3, 4. So we have pentane, but we have a double bond. So we have pentene, and we have a substituent here on our 4-carbon. So we have 4-hydroxy, pent-2-ene for the double bond. And then because it was a carboxylic acid, but it has a nitrogen on it, we drop the oic acid and add the word amide. Okay. And always the carboxylic acid carbonyl is the number 1 position. And because this substituent, this substituent is on the other side of the bond from this substituent, we have our trans. Okay. All right, everybody, take a little break. little bit of green tea. Okay, it's right about 9 o'clock. We're gonna do a little stretching, and then we're gonna head into our final 20 minutes here. Nomenclature is all about the process. Go to Canvas, download that nomenclature review and that functional groups. You'll see that the generalized forms and the naming structures are all there as well. And that prioritization list. Again, we'll be only going probably up to carbonyl, probably aldehydes and ketones this semester, because we hit those a little bit in alcohols. But then next semester, knowing all these things, it's going to make it really easy to shoot through those chapters that we have after it on the next semester, chapters 12 through 21. Okay, so let's name a more complex amide. So again, we do the first thing first. We try to find where the carboxylic acid is. And in this case, the carboxylic acid is going to be, let me try this, starting with the carbonyl here. And the fact that this is the electronegative atom tells us that that was where the carboxylic acid was. So this is our longest chain possible, giving us hexanoic acid. But we have a nitrogen on that. That nitrogen there changes the name to amide. So it's hexanamide. Okay, so that's our carboxylic acid side of it named. So we've named our parent chain. All this part right here is covered by hexanamide. Okay, we have a substituent on that chain, and it's in the 3 position. So we have that 3-ethyl. But wait, on the previous slide, we had 2 hydrogens on that nitrogen. Okay, meaning that it was a unsubstituted amine, unsubstituted amide, and we named it as the amide. However, we have a substituent on that nitrogen, but we only number the carbons. So how can we signify that there's a substituent on that nitrogen? Okay, the way we do that is we actually use a dash N dash. That's telling it whatever substituent follows is actually attached to a nitrogen and not the carbon chain. Okay, the number here tells us where it is on the carbon chain because we only number carbons. The N tells us that it's a substituent on a nitrogen. Okay, so we have our hexamide for our carboxylic acid with that nitrogen on it. We have our 3-ethyl because that's our substituent. And now we include our N-methyl here. Now note, the substituents are not labeled in a number, ordered in alphabetical order. So ethyl comes before methyl. The N acts like a number. You don't alphabetize the N. You only alphabetize the name of the substituent, okay? So if we were to put if we were to take this hydrogen off and put another methyl group here, we would have to show that both of those are on there, and you would do N, N dash dimethyl. And it wouldn't change the order because remember, di doesn't count when we're doing alphabetical order. Okay. So that's how we go from an amide to a substituted amide by denoting it's on the nitrogen. And if you had 2 substituents on that nitrogen, you do N. Okay. So let's name this one. We have 2 different substituents on the nitrogen. We have to figure out our carboxylic acid first. So that obviously is this one, and this nitrogen tells us that it's an amide. So we're going to have 1, 2, 3, 4, 5, 6 carbons. So we're going to have hexanamide. Okay, but we have an infix now. We have a triple bond in the middle, so we have to have our ine in there somewhere. So let's start numbering. We always number from our carbonyl carbon of our carboxylic acid, and we go to our alkyne is located at 3. Our methyl substituted is located at 5. And oh, let's not forget these 2 here. Okay, but let's name our main chain first. Okay, so our main chain is going to be that hex right here. We have an alkyne at 3, so 3-IN. And remember, we would have an E at the end if it was a hydrocarbon, but we drop that E and we have amide. Inamide is our N group here. So that's named the main chain. Now let's put our substituents in. We have a methyl on a 5. We also have a methyl on an N. Okay. Remember I said N is just like the number in the fact that it's not counted in alphabetization. So what we do is we can locate them together. If we have two methyl groups, one's on an N, one's on a 5, we use them together. Now we have another substituent here on the nitrogen here, and that's an ethyl group. And so what we'll have here is ethyl comes before methyl. So the first thing is N-ethyl dash 5 N, 5 dash dimethyl, and then our hex 3-ine amide. So again, we're just using that same set of rules to get things that seem to be more and more complex. Okay. So then the N does come before the numbers on these, by the way. So just in case. I have started recording the videos. I will start uploading them this weekend. By the way, there's a question chat there. Okay, so there's another cool derivative of carboxylic acid where what you do is you take one carboxylic acid and another carboxylic acid and you take away water from the middle. So when you take away water, it's called an anhydride. You've removed water, dehydrated it, an anhydride. And so when we name this, we call it an oic anhydride because it was oic acids and anhydrides. So in the case, if they're symmetrical, all you have to do is name the one side, or what is both sides. In this case, we have 3 carbons here. So that would be propionic acid. But because it's symmetrical on both sides, we call it propionic anhydride, signifying that we've removed water and we have 2 propionic acids attached together. Okay. If it's unsymmetrical, you name it you have to name both carboxylic acids in alphabetical order. Okay. So you have pentanoic for pentanoic acid, propanoic for propanoic acid, and hydride to tell you that they're hooked together. Okay. So it's naming the 2 carboxylic acid groups and then adding them together with that anhydride. Okay. And again, next semester, when you start doing these, go ahead and review the nomenclature review to make sure you have it. Okay. So there's another cool derivative here. I said that when we have electronegative atoms on a carbonyl, those were carboxylic acid derivatives. So in the case of this, we've replaced our oxygen and our nitrogen with a halogen. And when we replace it with a halogen, we call these acyl halides. Okay, we're going to use them a lot in chemistry, especially when we start doing reactions with benzenes. Okay, so what we're going to do is we're going to drop the E at the end and call it oil halide. So in the case of a simple one, where we have this right here, Cl, we have 1, 2, that would be ethanoyl chloride. Ethanoyl, because it's 2 carbons long, so it's ethane. We're dropping the E and adding oil, and then whatever the halogen is. And in this class, it's chloride. So here, we're going to have oil bromide right here. But we have some complications because we have a double bond. So we have 1, 2, 3, 4. So we're going to have butenoic acid that we've converted. So we have buta. The alkene is located on number 2. So 2-ene, oil, and then the bromide comes at the end, bromide right here. And we have no other substituents. So we're completed with our name, but we have to think about the stereochemistry on our double bond here. They're both on the same side of the double bond, so it's cis. Okay, so that is the addition of there. So every time you change the name of a compound, it's because you've changed the functional group of it. Okay, now I said when we had nitrogens that we had to locate the substituents on those nitrogens. So we're going to talk a little bit about that. So if we have just a nitrogen with no carbons on it, technically it is not an aromatic compound because it has no carbon-hydrogen bonds. Okay. However, if you take one of those hydrogens off and put a carbon chain on there, a single carbon chain on there, we call that a primary amine, because it doesn't matter what the nature of the carbon is, it's that you have one carbon-nitrogen bond. Okay, so amines are a little backwards from the priorities of alcohols and carbons and halogens. They all follow what the priority of the carbon is. Nitrogen is the only one who doesn't do that. Okay, and in this case, in the amines, we have one carbon chain on it is a primary amine. Two carbons attached to it is a secondary amine, and three carbons attached to it is a tertiary amine. Now that leads us to a couple different ways to name things, okay? But typically you would name it as an amine, okay? So if it's just an alkyl group, like a butyl group or a propyl group, you can name it simply with the group and add amine to the end. So ethylamine, propylamine, etc. Okay. So the fact that there's only one substituent on there indicates it's a primary amine. Okay. If you have two substituents on there, you have to denote that some way, either by saying dimethylamine, so you have two groups on there, or in the case, if they're two different substituents, you list both of them and you put them in alphabetical order. So this would be ethylmethylamine. Notice I'm not saying you don't have to put the ends here. You don't have to put the ends here because the name is amine, okay? The other one was an amide. You had to show that things were, these are amines, okay? In this case here, we would have dimethyl, diethyl, methylamine. So that's indicating we have three substituents on there, making it a tertiary amine. Okay. All right. So how do we name the amines? Okay. So if the amine is the highest functional group, it changes the name at the end by dropping the E and adding amine. Okay. So, and like our other rules, because it changed the name, we want to have it at the lowest number possible. So when we name this one right here, we name this as our position for our amine. So we're going to have two amine, but we have an alkyne. So we have to make sure our infix is correctly located at the 4-ine. And we have a total of 5 carbons, which gives us our pent. And our last thing is our substituent. We already have it numbered because of the amine, so we know it's our number 3. So we end up with 3-methyl pent -4 -ine -2 amine. Okay. Same rules. Okay. Now, when you have secondary amines, you have to name the longest parent chain first and all its substituents, and then you locate the other substituents on that nitrogen. So if we look at this as the longest parent chain with the amine on it right here is this 8-carbon chain. So we're going to have octamine. We have a double bond, so we have a 6-ene 2-amine, because this is on the 2-carbon here. So we have oct 6-ene 2-amine. Okay. Now we also have a chloro, we have a methyl, and we have an ethyl. Okay. So those are the, oh, we have another methyl down here. So we have a total of 4 substituents we need to locate. We had the number from here, and these substituents are both going to have ends on them because they're attached to the nitrogen. Now we alphabetize. Chlorine comes before ethyl, comes before methyl. So we're going to end up with 6-chloro right here, N-ethyl right here, and then N and 7-methyl, dimethyl, octa for 8, ene for the double bond, and 2-amine. Okay. Just add the rules together, Okay. All right, we have a couple more functional groups containing nitrogen here. Now, technically, the nitrile is a carboxylic acid derivative, because if you take an amide and remove water, you end up with this C triple bond N right here. And the C triple bond N is called a nitrile, okay? And so because it's a carboxylic acid derivative, it is fairly high priority. And we always start numbering it from the carbon of the triple bond, okay? Not the nitrogen of the triple bond like an alkyne. Remember, we only number carbons, okay? So from that right here, we're going to have a total of 6 carbons. So if we just had the 6 carbons and none of the other substituents, we would have hex a nitrile. Hexanitrile would be our name. We just would have the drop the E and add, hexane nitrile. Okay, so that being said, let's name this compound. We have a total of 6 carbons, so we have a hex. We have a triple bond, and we have it located at carbon number 5, so that's hex-5-YNE, and then the word nitrile. Okay, so it'd be hexane nitrile if it wasn't for the double bond, triple bond. Because of the triple bond, it's hexyne nitrile, sorry. Now we locate all our other systems. We have 2 methyl groups at 2 and 4, and we have a bromine at 3. So alphabetize that, 3 bromo, 2, 4 dash dimethyl hex 5-ine nitrile. Okay, so yeah, that's all the rules there. Okay, so one of the last functional groups I want to talk about is what we call the acyl functional group. Okay, we use this in a lot of different ways. We use this acyl group all the time in saying, oh, this is the acyl group is going to leave, this is that. It's a good leaving group, it's good for things, but it's based on the concept of it is this group of the, right here, the carbonyl with a CH3 group attached to some electronegative, some other atom here. Okay, so when we have it as the carboxylic acid, it's called acetic acid as the common name. That's where the acyl group comes from. And it's typically denoted AO, sometimes the acetate ion. This is AC is the acyl, acetate ion, and acetic acid. So this is why knowing the acetyl group is actually very important. Now, when it's attached to an amine, it's called acid amide. So the acetyl name is incorporated in there. When it's the aldehyde, it's called acid aldehyde. When it has a methyl group on it, it's a ketone, so it's acetone. So it'd be the acetyl group as a ketone, acetone. And when we have it as an ester, it would be the acetate. So it's onate as the O8 as the IUPAC name, it's 8 as the common name. So we have methyl acetate. And when we have it as the anhydride, it's acetic anhydride. So that acetyl functional group, that this little small function here is really important to know as a separate group. Then it can be attached to a variety of things. That's why in the notes here, it's a Z. It could be a bunch of different things. Here, it's just 6 different things already, but they all had that acetyl name in the group, in the functionality. Okay. All right. So let's tie everything together and talk about when we have multiple functional groups of the same thing. Just like when you have multiple substituents where we can use di, tri, and tetra, we can also use that for things like dienes, dialcohols, and carboxylic acids. What we do is we put the di, or the tri, in front of the OL, the oic acid, the nitrile, whatever it is, okay? So you can do that with the naming functional groups also, okay? So in this case here, we would have diol. Note, we have to note where both of those alcohols are. So we have the 2,3 diol. In this case here, we have a dicarboxylic acid, one on one end, one on the other end. So we actually have to name it for that. Now, this doesn't note where they are. Most carboxylic acids are, the dicarboxylic acids are at the ends, so, but you'll just number from one to the other. In this case, we number where the alkyne is the lowest number because it's the infix, and the substituent is the higher number. Okay. So how do we name things with multiple functional groups? Okay, whenever you think about multiple functional groups, you find the one with the highest priority first, and everything else is a substituent. So in this case here, the aldehyde is higher priority than the ketone or the alcohol. So that means we have to name it for the aldehyde. And so we have al at the end. Okay, so by naming this here, whenever we have a carbonyl that is not changing the name, we have to name it the oxo group. That's why we have the 5-oxo here. We have 6 carbons. We have an alkene located at our 3 position, 3 hydroxy. And now all we have to do is do our E and Z. We have our double bond, cut it in half, highest priority on this side, highest priority on that side, giving us our Zusammen, Zame-Zide. So it's Z. Okay. So with a little practice and following the rules in order, you can name very complex organic molecules and get them correct most of the time. All right, we're right here at 9:20. And that is my last slide for Module 2. Next time, we're going to start with acids and bases. Okay, any questions about nomenclature? I think on the schedule we have planned our first activity is going to be next week, and it's going to be nomenclature. Let me double check my schedule here for this class. It should be next Thursday, February 4th. We're going to have our group activity on nomenclature. Okay, so thank you very much. And if you have to leave, go ahead. I'm going to stop sharing and stop recording. And